Hello dear students, today we will be deriving the gravitational potential and intensity due to a solid sphere and for two different cases. As we have already finished the derivation for this for a spherical shell, uh, we will apply some of the concepts in this case. Before attending this class, it is I will advise all of you to go through the note again, so that you can follow the lectures properly. The lecture notes are already shared in the Google Classroom. So let us consider that we have a sphere like this. Is the center of the sphere, and this time it is a solid sphere. It is not a hollow sphere, and we have a point P outside. So we will first of all do case 1, that is the point P is outside. If I consider this to be small r and this to be the radius, so I will connect the center of the, let me just correct it. So this is the point P and it is outside the shell. This is the center of the outside the sphere, and this is the O is the center of the sphere, and this is the radius of the sphere, and small r is the distance between the center of the sphere and the point outside at which you are supposed to find out the gravitational potential and intensity. So the first case is that when r is very greater than or equal to the radius of the sphere. That means if the point is either outside the sphere or on the sphere. Okay, so this is the first case. So what we are supposed to make it mathematically convenient, what we are going to do, we will consider that this whole sphere is made up of large number of concentric spherical shells. So all of you can imagine that, suppose if I start with a solid sphere like this, and then if I keep on putting one spherical shell upon another, and if I keep on repeating this for number of times, finally I am going to have a solid sphere. And in this case we will consider that all the spherical shells, so the solid sphere is assumed to be made up of large number of spherical shells of masses m1, m2, m3, like that. Okay, so now since we are considering the solid sphere to be made up of large number of spherical shells, okay, and you can see this point P, whatever be the shell you consider, suppose you are considering this shell, you are considering this shell, or you are considering this shell, whatever shell you are considering, you are always outside the shell. Okay, so if I ask you, say this particular shell is of mass m1. Okay, then if I ask you that what is the potential at the point P due to this particular shell, okay, of mass m1, what will be your answer? For that you need to go back to the derivation for gravitational potential for spherical shell. And if you remember, the gravitational potential for spherical shell outside it was given by V equal to minus Gm by R. Okay, but interestingly this time we have so many shells. Now we have, suppose I will call it, so for the first that shell it will be Gm by r. Okay, then if I consider this shell, and if I consider this shell is of mass m2, so this is of mass m2, the potential due to that will be v2 equal to minus gm2 by r. Okay, so that means we can keep on repeating it for other shells also. Suppose if you want me to go for other shells, suppose we consider this shell again. Okay, so this shell is of mass m3, so potential at p due to the red shell will be g m3 by r. All right, so therefore this solid sphere is nothing but combination of all the shells. So therefore total potential, therefore total potential at P due to the complete solid sphere is V is equal to V1 plus V2 plus V3, like that. So it will be nothing but Gm1 by R minus Gm2 by R minus Gm3 by R, so on. So finally we can write G by R is common, so M1, M2, M3, like that. So this thing is nothing but the mass of all the shells. All the shells. So that thing nothing but mass of all the shells together make the solid sphere. So this is nothing but the mass of the solid sphere. Okay, so that means we can write it is G m by r, because total mass is nothing but small m by r. So this is the expression for I will denote it. I have not mentioned it capital M, right? Okay, so I will denote it as capital M. Okay, instead of small m, I will write it as capital M, where capital M is equal to m1 plus m2 m3 total mass of the solid sphere. Okay, so and as usual, if I want to produce the intensity, like gravitational field intensity, it is nothing but nebula vector v. So it is nebula vector, so minus G capital M by R. So it will simply be equal to minus capital GM. So it is nebula vector minus minus plus 1 by R. So it can further be written as minus GM by R square R cap.